The use of a slow precession rate gives us a problem at startup. On initial switch on, the alignment that the gyro takes up is random, and is unlikely to be in synchronization with the Earth's magnetic field. Therefore, an error signal is detected. The problem is that the precession motor's normal correction rate is designed to be only 3 degrees per minute, in order to smooth out short-term fluctuations. And if the gyro happened to be 90 degrees out, it would take 30 minutes to synchronize, which is obviously unacceptable. The solution is to have a rapid synchronization facility. This can either be a mechanical clutch operated by the pilot, as in the DGI, or, in later compasses, a high-gain mode for the precession amplifier, similar in principle to rapid erection in the electric artificial horizon. This is operated by a 2-position switch, spring-loaded to the normal position, which has to be held against the spring for rapid alignment. Operation of this switch increases the precession motor's correction rate, so that synchronization takes only a few seconds. More modern compasses are even more automatic. If a large error is detected, fast precession takes place at typically 60 degrees per minute until the error is 0. Then the system automatically reverts to the slow, smooth precession rate of typically 3 degrees a minute. We therefore have to modify our original block schematic to include the rapid synchronization facility. We still have 2 more lessons to come on the gyromagnetic compass, one on the flux valve and the other on the remaining components. But let's summarize what we've covered so far. The direct reading compass suffers from turning and acceleration errors, is situated close to the pilot, but also to sources of deviation, such as electric lights, electric motors, and ferrous metal, and is a self-contained instrument. It is not possible to take magnetic heading from it as an electrical or mechanical input into other instruments. In the directional gyro indicator, turning and acceleration errors are eliminated, and outputs can be taken to other equipment. But there is no magnetic monitoring. We therefore have a system which combines the best of both sources: the short-term rigidity of the gyro and the longer-term monitoring of the Earth's magnetic field. We looked at all the basic components. This system has several advantages over the direct reading compass and DGI. Firstly, the flux valve is usually mounted on a wingtip or on top of the fin, and is therefore well removed from most of the sources of deviation. On initial switch-on, the gyro is brought into alignment with the signal detected at the flux valve. From then on, the outputs of the gyro and the flux valve are compared. If there is any error, the gyro is precessed into alignment with the flux valve by the precession amplifier and precession motor. This overcomes the normal gyro drift. The flux valve on its own would still suffer from turning and acceleration errors, but sending the signal via the gyro gives stability and rigidity, because the precession motor applies corrections to the drive shaft at the rate of approximately only 3 degrees per minute. In a turn, both the flux valve and the gyro shaft turn at the same rate, so there should be no significant error at the end of the turn. If any error is generated in the turn, it will be small, and is precessed out in the normal way after completion of the turn. Finally, we modified our block diagram to include the rapid synchronization facility. This concludes the lesson. We will look at flux valve theory in the next session.